In this segment, we will be solving a problem from the kinematics, and this problem is related to um, constrained particle, a particle which is constrained to move on a particular path, and we will be using Cartesian coordinate to solve this problem. And the problem goes like this. As you can see, there is a track here. So this is the track which is given by this equation y is equal to 1.2 x squared, on which this yellow color peg, this is constrained to move, and at the same time there is a vertical slot that you can see here. This is the vertical slot in which this yellow color peg is constrained to move, and this yoke, the orange color yoke which contains this vertical slot, is um, capable of moving only in the horizontal direction, that is in the x direction. And what we are supposed to find out is the velocity and the acceleration vector of this peg. And at the instant when the yoke or the vertical slot of the yoke is at a distance of 0.27 meters from the y-axis in the negative x direction as shown, and at that particular instant the speed of the yoke is v, which is 2 meters per second towards positive x direction, and at the same instant the rate of change of speed of the yoke is 0.6 meters per second. So these are the given conditions, and we have to figure out the velocity and acceleration of the peg. For such problems, when there is a constraint given on the motion, generally we should start with the relationship between the y coordinate and the x coordinate as given here. So that's suppose I write, say, y is equal to 1.2 x squared. So this is the constraint. I can write like this. Otherwise I can also write the position vector r. If I consider the position vector r of the peg, I can write that as, say, x I plus 1.2 x squared j. Okay, now that could be the position vector, which we can represent like this. Now to get the velocity, we can always differentiate this r with respect to time to get r dot, that will be x dot I plus here if we differentiate with respect to time, it will become 2.4 x times x dot j. Right, now this expression in another way we can write as, just from this relationship, that y dot is equal to 2.4 x dot. Okay, now these are the two ways in which basically we can express the things. And similarly, acceleration vector we can write as, say, r double dot is equal to x double dot I plus, if we differentiate this now, it has got two terms, so we will get 2.4 x dot squared plus here we will get 2.4 x double dot in the j direction. So this whole thing we can keep it in brackets, and exactly in the similar way we could have written as, say, y double dot to be equal to 2.4 x dot squared plus 2.4 x double dot. I'll not write here, I need some space basically. Say 2.4 x x double dot. Okay, so these are basically the two ways in which we can write this side as a position vector and its differentiation, and the other one is just the relationship between the y coordinate and the x coordinate. What it tells you is that at any instant of time t, the x position is decided by this yoke. Okay, is decided by the yoke, and corresponding to that x coordinate, the y coordinate is decided by the track. So that's how the particle moves. Now and then what the point to be noted is all these expressions what we have derived here, they are valid for any time to come. That's very important to observe. So once we have got the expression, we can actually put these specific values at the instant of interest to get the values of velocity, acceleration, etc. So in order to do that, let's see. Okay, so when x is equal to negative 0.27 meters, our displacement y is equal to say 1.2 x squared, which is nothing but 1.2 times x is minus 0.27, its square is equal to, it will come out to be 0.0875 meters. Now this we can write as in a vector form. If we want to write, we can always write like this. Say r is equal to minus 0.27 27x, not x, in I, right? So I plus 0.0875 j. Now exactly in this way we can use equation 2. I'll give names maybe to the equation. So this is say 1, so this is say 2, and this is say 3. I can now use equation 2 to get say the y dot, which is equal to 2.4 x dot. So this is equal to 2.4, x is our minus 0.27, and x dot. Now x dot is nothing but this the speed at which the yoke is moving, right? So this is nothing but x dot. So here we will write 2, and this will give us minus 1.296 meters per second. Okay, so and like the earlier case, we can now write the velocity vector to be say r dot is equal to it's 2I minus 1.296 j meters per second. Now going back to the acceleration, we can again use equation 3 and write that y double dot, the acceleration in the y direction, the vertical direction, is equal to say 2.4 x dot square plus 2.4 x double dot. So that will give us 2.4 times x squared, x dot squared is 2 squared, and plus 2.4 times x is a minus 0.27 times x double dot. Now x double dot is the change in rate of change in speed, so this is x double dot. So here we will put 0.6 and this will come out to be 9.21 meter per second per second. Here I have made a mistake. Here it should have been meter per second squared, right? So it should have been meter second squared. Yeah. Now, so what we should do is, yeah, we can write now the vector form of the acceleration, which is say r double dot is equal to now 0.6 I plus 9.21 J meter per second squared, right? Now so I can write here the velocity vector is this and the acceleration vector is this. In fact, you can calculate even now the acceleration, which is perpendicular to the track and the tangential to the in a direction tangent to the track. So that you can get by just observing that. If I draw, say, wait, I'll suppose this is a vertical, so perpendicular direction vector here, and it makes an angle, say, beta here, and this one here will be the tangent direction. Okay, if this angle is alpha, so we can calculate the magnitude of tan alpha by, so tangent of alpha is nothing but we can calculate dy over dx at that particular location when x is equal to minus 0.27, and in fact we can get the absolute value of this, which will come out to be 0.648. That will give us alpha to be equal to 32.94 degrees. That makes beta to be equal to 57.06 degrees. From there, we can always calculate the accelerations in the normal and tangential direction. See, for example, here a unit vector in this direction, okay, if we call this say en, okay, if this is en and this is et, okay, now en et we can write like this. So en is nothing but cosine of say 57.06 degrees I plus sine of 57.06 degrees J. Okay, so that's equal to 0.544 I plus 0.839 J. Then we can calculate the acceleration in the normal direction to the track. Its magnitude basically is equal to the acceleration which we have got now. So this acceleration, that is 0.6 I plus 9.21j. So this we will dot with this en. Okay, that if you do, you will get 8.05 meters per second square. And then we can actually write the an vector. So I'll put this as an magnitude, and an vector will be nothing but this 8.05 times 0.544 I plus 0.839j. So this is the a normal, and similarly you can calculate a tangential also. Okay, so this is it, and so we will see in next segment one more problem. See you then.